Hello, today me and my group mates will be explaining on the textile manufacturing plants and the waste treatment process that we designed. Next, the raw materials needed for in the textile industries are cotton, jute, silk, wool, and man-made fiber. Next, the textile process has 7 steps, which are fiber production, yarn production, fabric production, pre-treatment, dyeing and printing, finishing treatment, and the manufacture of end products. Next. Now we have the block diagram of the textile production with waste that are produced after each step. The manufacture of fibers is placed in various ways and all textile which provides the required strength, durability, look, and texture. This can be divided into 2 types of fibers, which are natural fibers and man-made fibers. The next step is the manufacturing of yarn, where we use the spinning process. Fibers are spun into a yarn where oil is added to the fiber to increase strength, cohesiveness, and reduction of friction. Next is the manufacturing of fabric, where there are different types of procedures such as weaving, knitting, and turfing. The next step is the pre-treatment, which is accomplished by a multi-step procedure depending on the type of fabric. These steps are such as sizing, scoring, bleaching, and mercerizing. After pre-treatment, dyeing and printing takes place. It is then continued with finishing treatments where the fabric technical characteristics are enhanced depending on its required features. Lastly, it is the manufacture of products, and this is where the products such as sweaters, jeans, shoes, carpets, and many more are produced. Now I will pass the mic to Abdallah.
All right, thank you, Darwish. So let's speak about the waste produced. A lot of clothing and textiles are thrown away each year in the United States. Up to 31 kilos per year of waste packaging, scrap material, lint, and yarn in knitting. As far as the wastewater is concerned, the TSS trend is to be over 100 ppm, which is a visible trend in emission of gases in the United States. 5.9 kilograms of CO2 is actually required to produce 1 ton of conventional cotton, while 2.35 kilograms of CO2 is required to produce the same quantity of organic cotton. So let's go to the next slide, which is about environmental impact. Water pollution. Due to the dyeing and the finishing products, textile industry is considered to be the most responsible for around 20% of the worldwide clean water contamination. Each year, washing synthesis is estimated to release 0.5 million tons of microfibers into the ocean. World carbon emission. The fashion industry is expected to contribute up to 10% of the global carbon emission, which is more than international flights, marine shipping combined. And according to the European Environment Agency, the textile sales in the EU created 654 kilograms of CO2 emission in the year 2017. So the next slide is about waste management. So from fiber cultivation and manufacturing to transportation and to the life cycle analysis, every facet of the textile industry is concerned with sustainability. Here are some waste management examples from the textile industry. Firstly, composting. Industries may focus on the products that are 100% natural and that could be disintegrated completely when dumped into landfills at the end of their life cycle. Secondly, regeneration, a process that involves employing heat and chemicals to renew the fibers from the natural resources, such as wood, in order to create fabrics with long-term sustainability. And lastly, alternative to paper making. Papers are manufactured from old fabrics. This is a time-honored technique for making high-quality paper. And this is very critical to help prevent deforestation. And now I'll be passing on to my group member, Tyre.
Thank you, Abdullah. This is the block diagram of the treatment process my teammates and I have come up with. In essence, raw wastewater from the dyeing sector is fed into clarifier number 1, where no alum is added, since this is the pre-treatment step, which precedes the chemical and biological treatment processes, which I'll get into later. Sludge is formed by suspended solids that settle at the bottom of clarifier number 1. Effluent is then fed into clarifier number 2, where the chemical treatment commences. Alum is added as a coagulant, which forms chemical sludge in addition to the sludge formed by suspended solids. The sludge from clarifier number 1 joins the sludge from this clarifier and ends up in a sludge tank. Effluent is then fed into the biological treatment process where the BOD, the biological oxygen demand, is reduced by microbes and water is discharged. From lecture 6, slide 5, as the basis, it is assumed. Next. From lecture 6, slide 5, as the basis, it is assumed that 20,000 cubic meters per day of wastewater is fed into the system. The mass of chemical sludge can be found using the stoichiometric equation, which is shown in green here. It's also assumed that the TSS removal without alum is 64% and with alum 82%. Next slide. I would say that the chemical treatment process complies with Standard B, which states that the TSS can be 100 ppm at maximum and the BOD can be 40 ppm at most. So it is shown that at the end of the day, the TSS is 32.36 ppm, while the BOD is 29.75 ppm. So the volume of sludge formed in the clarifiers can be found by finding the mass of TSS, which settles at the bottom, divided by the density of the sludge times the composition of the sludge. In this case, it's 8% of the mass. Similarly, when it comes to clarifier number 2, the influent flow rate is the influent flow rate is subtracted from the 20,000, so that we get here about 19,000 cubic meter per day. Other than that, the sludge tank volume is calculated to be around 141 cubic meters per day. Next slide.
Moving on to the biological treatment process. As you can see on the right, standard B for COD for the textile industry is 250 ppm. Our initial COD is 1,907 ppm, and the flow rate is 19,858.33 meter cubes per day. So in order to calculate the oxygen used, we have to assume some values, which is the COD of the cell tissue is assumed to be 1.42 grams of COD per gram of VSS, which is volatile suspended solid. the biomass yield, which is 0.42 gram VSS per gram of COD removed. Next, we must calculate the COD in, which is done by multiplying the initial COD by the flow rate. Then we will get 37.87 times 10 to the power 6 grams per day. The COD out is calculated by multiplying the standard B, which is 250, by the flow rate to get 4.96 times 10 to the power 6 grams per day. The biomass in COD is calculated by getting the biomass in gram VSS and multiplying it by the COD of cell tissue, which then we will get 16.82 times 10 to the power 6 grams COD per day. Finally, the oxygen used is calculated by taking the COD in and minusing it by the COD out and the biomass in COD, which will then get 16.09 times 10 to the power 6 grams per day. On this slide, you can see the references we have used to create this presentation. Thank you very much.
And
All right.
this is it for our presentation. Thank you for watching.